Give like another minute. Not that you have to finish them, just give me another minute.
So when you're finding like f of x, what you say? I feel like you have a y as a constant.
Right, or basic, or anything that's not x. So if there's more than just x and y, any not x thing would be treated like a constant. Excuse me. All right, let's see what we get here. So our function f of x, y is x to the fourth plus sine of y plus x squared times y to the fifth. We want to find del f del x or fx. We're treating y like a constant. So the derivative of x to the fourth is 4x cubed. The derivative sine of y is just 0. There are no x's there. And then the derivative of x squared times y to the fifth is going to be 2x times y to the fifth. Because when you have constant multiples, they just hang out. And of course, I wouldn't actually write the plus 0. I would just write this as 4x cubed plus 2x times y to the fifth. And honestly, I would probably, I don't know about the order we do things in, but I might just go straight from there to doing fxx. I've already found fx. If I take the derivative of that again with respect to x, I can kind of stay in the same mindset. So, okay, well, fxx is going to be derivative of 4x cubed is 12x squared, and the derivative of 2x times a constant is 2 times that constant. We'll do the same thing for fy and fyy. For fy, well, now x to the fourth is acting like the constant, so the derivative of x to the fourth is 0. The derivative of sine of y is cosine of y. And the derivative of x squared times y to the fifth. Now the x squared gets to pretend like it's a constant. And the derivative of y to the fifth is 5y to the fourth. And then I would, not required, you can probably leave it like this. I would probably make it look a little nicer, right? As cosine of y plus 5x squared y to the fourth. Not necessary. Yeah, Josh. Well, that's an excellent question. And it's because one of them is on its own, while the other one is multiplied by something that's a variable. It's kind of like the difference between taking the derivative of, say, like, I don't know, an example here, 6 plus 5x squared. Well, what's the derivative of 6? Right. What's the derivative of 5x squared? Right. But I really would like you to see that as 5 times 2x. Why wasn't the derivative of 5 0? Because it's a multiple of the thing that's a variable. So when you have a constant times a function, that constant, as I like to say, gets to hang out. Constants hang out if they're multiplied. If they've got variable friends, constants get to hang out if they have variable friends. If they're just by themselves, then they go home to 0. I mean, that's not a great analogy, but so over here, yeah, the derivative with respect to y of x to the fourth is 0, but the derivative of x squared times y to the fifth is x squared times the derivative of y to the fifth. And let's go ahead and do fyy as well. So here's our fy. Let's take the derivative of that with respect to y again. So the derivative of cosine of y is negative sine of y. And the derivative of 5x squared times y to the fourth, well, the 5x squared is a constant, gets to hang out, and its friend y to the fourth, we're going to take its derivative and get 4y cubed. And I would, again, probably simplify this as negative sine of y plus 20x squared times y cubed. Probably not necessary, but I think it is. Okay, so now for fyx, or del squared f del x del y, this is where we do y first and x second. So if we look at y first, here's fy, and then from here, I'm going to take the derivative of that with respect to x. So you can write that down if you want to. I don't think you need to. I would probably just write it as, okay, I'm taking the derivative with respect to x of my fy, which is cosine of y plus 5x squared y to the fourth. Derivative of cosine of y with respect to x is going to be 0. Derivative of 5x squared times the constant y to the fourth is going to be 10x times y to the fourth. So we're just getting 10x y to the fourth. And our expectation should be that the mixed partial derivative the other way will end up being the same. Let's check and see though. We do fxy, which means we take the derivative with respect to x first and then y second. That's going to be the derivative with respect to y of our derivative with respect to x, which was 4x cubed plus 2x times y to the fifth. When we do that, the derivative of 4x cubed, well, it doesn't have any friends that are variables, so its derivative is 0. And there are 2x times y to the fifth. Well, the 2x is to hang out because its friend is a variable, and the derivative of y to the fifth is 5 y to the fourth. And we get the same thing as the other way. You still get 10x times y to the fourth. So your mixed partials should equal each other in this class always. I would say other things, but really that's the truth. In this class, you're never going to see a function where they're not equal to each other. Which is nice because then when we later on we have to find either one of them, either fxy or fyx, it doesn't matter which one you find because they're going to be the same. Questions? Can we do more partial derivatives? I feel like we should. Let's get practice. Let me give you guys. I'll do one and then I will give you guys another one. Let's see, where'd you go? Had a good example. Did I lose it? No, not you. Yeah, that's a fine example. Sure. Let's say we want to do. So I'm just going to write this as find all the first and second partial derivatives, meaning the two first derivatives and all 4 second partials, whether they are mixed or just fxx or fyy. So find all the first and second partial derivatives of, let's see our function. Let's make it a little more interesting here. F of xy equal to, so let's say it's x to the 6th times e to the y cubed. It's going to be fine at first. So I'm always going to start with fx because x comes before y in the alphabet. Really, like honestly, that's why we usually do x before y, is because alphabetically it comes first. Fx shouldn't be too terrible. It's going to be the derivative of x to the 6th, 6x to the 5th, times e to the y cubed, just acting like a constant, hanging out. Cool, we're done with that part. Let's find y. So the x to the 6th now gets to hang out. And the derivative of e to the y cubed is e to the y cubed times 3y squared. I use the product rule. Or sorry, the chain rule, apologies. All right, let's do fxx. Fxx is going to be, I'm looking at fx and thinking, okay, whatever fx is, just take the derivative with respect to x again. So now, the derivative of 6x to the 5th is 30x to the 4th. And the constant multiple here still sticks around. I still got to e to the y cubed. On the other hand, fyy is going to be a little bit uglier because if I want to take the partial derivative again with respect to y, I'm going to have to now use the product rule because I have e to the y cubed times 3y squared. So if I was doing this, here's probably how I would do it. The x to the 6th is just a constant. It's going to hang out in front of everything else. And then inside here is going to be the product rule for e to the y cubed, which I might call g, and 3y squared, which I might call h. Not at all necessary to write this down. I just like to show my work so that you'll. Then I'm expecting to get g prime times h plus h prime times g. My g prime, the derivative of e to the y cubed is e to the y cubed times 3y squared. I feel like the thing that gets confusing about this particular thing where you have like the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and then you take the derivative again, you kind of feel like you've already done the other part of the product rule, but you haven't, right? We need e to the y cubed times 3y squared times another 3y squared, because that's your h. And then the other way, we need e to the y cubed, that's your g, and then the derivative of h is going to be 6y. So it can get a little bit messy. And I probably wouldn't bother simplifying that. We could, I don't think you need to. I'll say the exception is if you're trying to set something equal to 0 and solve for it, then usually simplifying it as much as possible is a good idea. All right, let's look at the other side of things, not the other side, but the mixed partial side. So from fx, let's go ahead and also do fxy. So now I'm looking at fx, I'm going to differentiate with respect to y. So now the 6x to the 5th gets to hang out. And the derivative of e to the y cubed, you've already done a couple times. It's going to be to the y cubed times 3y squared. Not too terrible. And for fyx, I would do the same thing. I would look at fy. I'm going to take the derivative of that with respect to x. So all this stuff here with y's in it, it's going to hang out. The derivative of x to the 6th is 6x to the 5th. And the e to the y cubed times 3y squared is just getting to sit there. And that's good because they should be the same, and they are the same. We're happy about that. It's often a good check to see if you've done things correctly that these should equal each other. Right? If you've somehow gotten the fyx and fxy are different than each other, you need to go back and check your work because something probably went wrong somewhere. Okay. Yeah, we can do that. Let's do that one. So I want you all to try this one. So for, I want to do that. Yeah, that's kind of gross. Sorry, I'm trying to, oh, no, that one's really, I definitely don't want that one. Apologies. Let's try this one. Let's say our function is f of x comma y equal to 6x squared plus 6y squared is 3x squared y minus y cubed. Go ahead and find all the things. Find x, y, fxx, fyy, and then the mixed partials. I will point out, not that it's super duper important, but I am not saying f of x, because f of x is like f parentheses x. I'm really saying fx, nothing in between, because that's usually the way we say these partial derivatives. You can also say it the longer way, del f, del x. So nobody wants to say all that. So I would say fx, fy, et cetera, et cetera. All right, go for it. Maybe like 2 or 3 minutes. All right, let's go ahead and take a look at these. So fx shouldn't be too bad. It's 12x plus 0 minus 6xy minus 0. Fy 0 plus 12y. Derivative of minus 3x squared y is minus 3x squared. Derivative of y cubed is minus 3y squared. Okay, seems all right. For fxx, we're just going to get 12 minus 6y, right? Sorry, I almost said 12. All right, derivative here is 12. Derivative here is minus 6y. So the derivative of x is just 1. And then for fyy, 12 minus 0 minus 6y. Interesting. And then for fxy, taking the derivatives with respect to y, we're going to get a negative 6x. And then for fyx, taking the derivative with respect to x, we're going to get a negative 6x. There's some reasons some of these things are coming out to be the same, which are not that important, but are interesting nonetheless. So this example, not that hard, but it actually brings us to something that is relatively interesting, which is that we can take these partial derivatives and then use them to find the relative extrema of this function of 2 variables, of this surface. So I want to just point out, let me go back a minute. So if you had a very basic looking kind of like downward opening paraboloid, we can see it has a relative maximum right there at the top, right? That point is bigger than all the points around it. And if you think about it, the plane that would be tangent to this point is horizontal, right? If it's at the very top, your plane isn't tipping one way or the other, because if it was tipping one way, you could kind of go up in that direction to then have a plane that was flat. But what you can kind of think about here is that on this plane, both the derivative in the y direction and the derivative in the x direction, well, they're both horizontal things. Those derivatives are both equal to 0. So the thing to be aware of here is that when you find the points where both the partial with respect to x and the partial with respect to y are equal to 0, that is the critical point of your graph. And it might be where you have a relative maximum. It might be where you have a relative minimum. Or it might be where you have a saddle. Right here, even though it's going to be not a great drawing, right here you do have a tangent plane that is also horizontal at that point there. It's kind of cool. So what we're going to do is we're going to take this function and we're going to find the critical points. And the way you find the critical points is by finding all the x and y values where both fx and fy are equal to 0. So here's the real truth. We're usually going to find these by starting with the easier equation. So if I was going to deal with one of these, I would start by setting that one equal to 0 because it's a little easier to solve. If I set fx equal to 12x minus 6xy equal to 0, what can I factor out? I think I factor out a 6x. I'm left with a 2 minus y. So my solutions are either going to be x equal to 2 or, sorry, x equal to what? Is x equal to 2 a solution? No. What should x equal really? Right, x should be 0 and y should be 2. And I want to stress here, x equal to 0 and y equal to 2, that point is not a critical point. If you plug in 0 for x and 2 for y, you get 0 here, but you don't get 0 here. So I want to really, really stress, to be a critical point, it has to be a point where both this partial derivative and this partial derivative are equal to 0. I'll even point it, right, if we actually plug this in, if you plug in x equal to 0 and y equal to 2 into your partial with respect to y, you're going to get 12 times 2 minus 3 times 0 squared minus 3 times 2 squared, which is 24 minus 12, which is 12, which is not 0. I'm making this extra clear because people often make this mistake. They're saying, oh, I got an x and a y from this. That's a point, not a point. What we're going to do is we're going to take each of these possible solutions and plug them into the other equation. I'm going to take fy, I'm going to plug in x equal to 0. So if I plug in x equal to 0, I'm going to get 12y minus 0 minus 3y squared. I'm going to set that equal to 0. Factoring out of 3y, I'm left with, bless you, 4 minus y squared. So I either get y equal to 0 or y equal to plus or minus 2. So just from x equaling 0, we have 3 possible critical points. We get 0, 0, we get 0, 2, and we get 0, negative 2. We're also going to plug in y equal to 2 because that's also something that will work. And of course, I run out of room here, so let's go to the next page. So if I plug in y equal to 2, so my fy is going to now be 12 times 2 minus 3 times x squared minus 3 times 2 squared. And I want that to equal 0. So I've got, let's see, 24 minus 12 is 12 minus 3x squared equal to 0. I'm going to get 3 times 4 minus x squared equal to 0. So I'm getting either x equal to plus or minus 2. So here I'm getting, if y equals 2, x could be 2, or x could be negative 2. You have to look back. I feel like I made a silly mistake somewhere, but I don't really think so. Oh, I did make a mistake somewhere. It was easy to miss because I was going kind of fast. So when I factored here, I had a 12y minus 3y squared. I factored out a 3y, and I have a 4 minus, should have just been y. You see that? Because y times y would give me the y squared. So sorry, I didn't mean to make that mistake. I mean, I usually don't mean to make mistakes. So here we really don't get y equal to plus or minus 2. We actually get y just equal to 0 or y equal to 4. So neither of those should be critical points, but 0, 4. Okay, so just want to point out we have 4 critical points. We have 0, 0, 0, 4, 2, 2, and negative 2, 2. And just so you all can see it, because I think it's worth seeing, if we look at our partial derivatives again, so our partial derivative fx was 12x minus 6xy, or if you prefer, and I do kind of prefer 6x times 2 minus y. And our y partial derivative was 12y minus 3x squared minus 3y squared, which I suppose you could factor out of 3 if you really wanted to and get 4y minus x squared minus y squared. But if you plug in any one of these points to both of these equations, both equations will equal 0. Plug in 0 for x, well, this one will definitely be 0. Plug in 0 for x and 0 for y, yeah, 0 minus 0 minus 0, definitely 0. Plugging in 0 for x and 4 for y. Well, 0 for x still gives you 0 here, and plugging in 0 for x makes that go away. And plugging in 4 for y, 12 times 4 minus 3 times 4 squared is going to be 48 minus 48, which is 0. Works here too. If you plug in 2 for x and 2 for y, well, could if I plug in 2 for y right there, that's going to be 0. Plug in 2, 2, and 2, I get 12 times 2 is 24, minus 3 times 4 minus 3 times 4, which is 24 minus 12 minus 12, which is 0. And lastly, same thing is true if I plug in negative 2 and 2. Still, y being 2 makes this 0. If x is negative instead of positive, you're still squaring x, so you're still going to get the same result. So I just want to make it absolutely 100% clear that these 4 points and only these 4 points are the points that make both fx and fy simultaneously equal to 0. And these are the candidates for things that could be where we have a relative maximum, relative minimum, or a saddle point. So the question becomes then, how do you check? So it's kind of, but not exactly the same. No, it's actually not really kind of the same. It's not the same as how we did in 16a. 16b, 16a. However, whenever we did it before, when we found like a relative maximum of function of one variable. The idea here is going to be, we're going to calculate a thing, and then based on the sign of that thing, we might have to do one more thing to then see if we have a maximum, a minimum, or a saddle. Here's the thing we're going to calculate. We're going to calculate what people typically call a capital D, and we'll call it gamma. One person last quarter called it gamma. Like, that's weird, but some people call it gamma. But here's what D is equal to. It's equal to the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. It doesn't matter which mixed partial we use because we know they're both the same. So in this particular example, our capital D, by the way, D stands for determinant of the Hessian matrix. It doesn't matter, but in case you're wondering why it's called D, that's why, because it's the determinant of some matrix. That's going to equal, so our fxx was, I'm just looking back at my notes here, was 12 minus 6y. My fyy was also 12 minus 6y. My fxy was negative 6x. So was my fyx. Negative 6x. And I think most of the time it is not in your interest to simplify this at all. We're just going to think about what happens when we plug in the points. So I'm going to plug in 0, 0 to this D thing. If I plug it in, I get 12 minus 0. That's really like hiccupy. Burpee, hiccupy. 12 minus 0 times 12 minus 0. So I get 12 times 12 minus 0 squared, which is 144. So if your D is positive, then you have to check one more thing. You have to check either of the second derivatives, meaning either fxx or fyy. I will point out that when D is positive, fxx and fyy had to have been the same sign. Let me show you why. If you look at this thing here, if this whole thing is positive, well, you've got something times something minus something squared. If these were opposite signs, that would be negative, right? A positive times a negative or negative times positive negative. And a negative minus something that's for sure positive is going to get more negative. So if these are opposite signs, this could not have been positive. So we know that if it is positive, they're both the same sign. Has to be true. There's no other possible. And they are, right? And this one here, they were both 12 and 12. So you look at one of them, people usually default to fxx. Then we're going to check, and we're going to see that in this case, fxx is positive. And if your second partial is positive, well, you probably don't remember, but you might. Back in either 16b or 16a, we learned what's called the second derivative test for a max or a min, where if the second derivative is positive, you have a minimum. Second derivative is negative, you have a maximum, because the second derivative is talking about the concavity. If your second derivative is positive, you're concave up. If you're concave up, that means your critical point is at the bottom of that parabola. Like I always think of a parabola. You're at the bottom. So if your second derivative is positive, you have a minimum. Second derivative is negative, concave down, maximum. So we're just checking out. We're saying, oh, if fxx is positive, then we have a maximum. Sorry, minimum. Oh my gosh, it's easy to say the wrong thing there. It's positive, opening up, minimum. And I should say relative minimum. On the other hand, if fxx ends up being negative, then we are concave down and we have a relative maximum. So here, where your d is definitely positive and your fxx is also positive, we have a relative minimum at 0, 0. 0, 0 is a relative minimum. Let's look at how it happens at 0, 4. So I'm going to calculate, I should have left myself a little more room here. The d of 0, 4 is going to be, well, plugging in 0 for x and 4 for y. 6 times 4 is 24. 12 minus 24 is negative 12. Again, a negative 12. And if x is 0, I'm just subtracting 0 again. So I'm still getting a positive result, which means it's either a maximum or a minimum, but now our fxx is negative. So we see that we have a maximum because it is concave down at this relative extreme. So we definitely have a relative maximum. So I'm going to back it up a little bit. If d is positive, you either have a relative maximum or a relative minimum. If d is negative, in fact, let's see the next one here. If we plug in 2, 2, I'm gonna move this one down a little bit. So 2, 2, the d of 2, 2 is going to be 12 minus 12, which is 0, times 12 minus 12, which is 0. If both fxx and fyy are 0, it probably means it's not going to be a max or min. But if we're plugging in 2 for x, we're getting minus negative 6 times 2 squared. And that definitely has to be negative. There's no way that can be positive. Negative or positive squared is positive, and then minus a positive is negative. This is going to be negative something, which is negative. So if d is negative, you have a saddle point. Nothing else to check. And the same thing's happened over here. Let's check. You plug in negative 2, 2. Oh, sorry, I was going to write the saddle. I have a saddle at 2, 2. And then finally at negative 2, 2, I think we're getting the same result, but let's check. I plug in 2 for y, I'm getting 12 minus 0, 12 minus 12 times 12 minus 12, which is again 0 times 0. I'm plugging in negative 2 for x, I'm going to get negative 6 times negative 2 squared. Still going to give me the same result. Still going to equal negative 144, which is negative. So also a saddle. Lastly, sadly, if d happens to equal 0, the test is inconclusive. meaning we don't know if that point is a maximum, a minimum, a saddle point, something else that's weird. So usually we hope that D isn't 0. Inconclusive. But it does happen occasionally. Question, Josh. Sure. So both 0, 0 and 0, 4 had a D value that was positive. But the difference here is that at 0, 0, the second derivative with respect to x or y was positive. If you plug in 0, 0 to, let me write down to remind you, fxx is 12 minus 6y, fyy actually happens to be exactly the same, which is not always true. If you plug in 0, 0 there, you're going to get a positive. So fxx at 0, 0 is just 12, which is positive. And if d is already positive and then either second derivative is positive, we have a relative minimum. On the other hand, if I plugged in 0, 4 instead, d is still positive, but when you plug in 0, 4 to the second derivative there, well, 12 minus 6 times 4 is 12 minus 24, which is negative 12. So it wholly depends on, so I should say, after d is positive, then it wholly depends on what's going on with either one of these second derivatives, either fxx or fyy. On the other hand, if d is negative, you're done, you get to stop, you have a saddle point. Ryan. So the reason we don't, when you're checking for a max or a minimum, is because they're the same. So remember just a few minutes ago when I was talking about how, like, if d is positive, we know for sure that fxx and fyy are going to have the same sign. That's why we don't check both of them. Because if I've already checked fxx, I know fyy is going to have the same sign. Now, again, that's only ever true if d is already positive. So, but if we know if we know that d is positive, we only have to check one of these two things to see if it's a max or a min. Because checking one of them is a tantamount to checking both of them. And then, just for fun, I'm being relative here. You can kind of maybe see a thing. Maybe. Oh gosh, maybe we could have. Wow, I really just blew it. Sorry. Let's go back. Let's go home. So I think we can all probably see that there definitely is a minimum at 0, 0. Right? At the origin right there, we were certainly bottoming out. And then we're also supposed to have a relative maximum to 0, 4. Oh, 0, 4. It's we can't see it. We got to scroll out. And that's kind of wonky. So maybe as, you know what I could do? Wait, let me do something really smart. I'm going to just scale this by a factor of like 1/10. That might make it easier to see what's going on here. I think that does. It just makes my outputs a tenth as big. And now that's kind of nice, yeah. So you can kind of see over here at 0, 4. Oh, look, there's your relative maximum right there when x is still 0 and y is 4. And then hard to see them, but you can kind of see the saddle points as well at 2, 2 and 2, -2. But they're, I'm a liar. Oh, I'm not a liar, but I'm just pretending like your vision is much better than mine. I can't really see them, I'll be honest. They're hard to see, but they're there. They're just kind of not easy to see. So yeah, so at least you might kind of believe that what we're doing here works. Actually calculating this stuff shows you how to find relative maxes and relative mins. It's kind of neat, I think, personally. We got time. Let's do one more example. It's also good practice of taking partial derivatives. So let's do one more example. And let me see, which function do I want to do? We can do that one. That one's not too terrible. The nice thing about, I will say this, is usually the functions themselves are not too heinous to take the partial derivatives of. So let me give you all this one. Let's say we have f of xy equal to, make sure that's not going to be terrible. Yeah, I could look over here real quick. I can give you something that I know it's not going to be terrible. Sure, let's pick something easy. Let's say we've got x squared plus y squared minus 2x plus 4y plus 3. I want you to find all 6 of your, well, you could find like, not both fx, y, and fx, but find them all, and then find your critical points. So after you find fy, fx, fy, fxx, fyy, fxy. Then after you do that, set fx equal to 0, fy equal to 0, and solve. You should only get one critical point for this example. All right, I took my partials. Fx was 2x minus 2, y was 2y plus 4. Xx was kind of boring, it was just 2. Fyy was also kind of boring, it was 2. Fxy is 0. I guess I should also write fyx is 0. So now to find the critical points, we're going to set each of these first derivatives equal to 0. 2x minus 2 equals 0, and 2y plus 4 equal to 0. So solving this, I get 2x equal to 2 or x equal to 1. Let me stress, x equal to 1 is not a critical point. It's half a critical point. We need the x and y coordinate to have the entire critical point. Unlike in 16A or B, where we found critical values, where it was just the x value, and then you found the y coordinate as like the output. Here, the z coordinate would be the output. Solving this one, 2y equals -4, y equals -2. So our critical point is the xy coordinate 1, -2. And here's what's less exciting about this one versus the previous one. We're going to find our capital D, but we're not going to have anywhere to plug in our point. So capital D being fxx times fyy minus fxy squared. In this case is 2 times 2 minus 0 squared. So capital D is definitely positive. And no matter what point we're plugging in, fxx is also positive. So whatever critical points we have in this, there's only one of them, they're definitely going to be relative minima. So the point 1, -2 is a relative minimum. Really what we have here is we just have a an upward opening paraboloid that has been shifted 1 over into like 1 in the x direction and -2 in the y. So it's really just your usual kind of upward opening paraboloid that has just been moved a little bit. I suppose you could see it if you really wanted to see it, well, or not, maybe. There we go. This one will actually probably not look too terrible. We graph it. We have z equal to x squared. I guess it didn't want the other one to go away. That's fine. Plus y squared minus 2x plus 4y plus 3. Yep, there's our upward opening paraboloid. And that point there, that is the point where x is 1 and y is -2. Because we've gone +1 in the x direction and -2 in the y direction to get that point there. Cool. I like it. Okay. We have time for one more. We have time for one more. Yeah, we have time. So let's look at one more example where things are a little bit weirder. Let's say, let's say we have f of x, y equals x cubed minus 3xy plus y squared. And again, so usually if someone writes this kind of question, what they'll say is find and classify all critical points. We usually don't find all the derivatives at first. Usually we just start off by finding the first partials and setting them equal to 0 and see what we get. So finding partial with respect to x, we're going to get 3x squared minus 3y equal to 0. And finding fy, we're going to get 0 minus the 3x is a constant, the derivative of y is 1, so we're going to get a minus 3x plus 2y. And here's what's disappointing about this system of equations. There aren't any immediately obvious values that any one variable has to have. Like we're not getting x equal to 1 or y equal to -2 necessarily. We're only getting relationships between x and y. When that's the case, you typically have to solve one equation for one of your variables and plug that into the other one. Here, it probably doesn't matter which one we pick. I feel like the second one's actually, the first one's gonna be a little bit easier to solve for y just because, well, I won't have fractions if I do it this way. So I would probably take this and say 3x squared equals 3y, and then divide both sides by 3 to get x squared equal to y. I'm going to take y equal to x squared and substitute it into the other equation for y. So I'm going to get that negative 3x plus 2 times x squared equal to 0. And I can factor out an x. I'm left with negative 3 plus 2x. So I either get x equal to 0 or negative 3 plus 2x equal to 0. So 2x equals 3. So x equals 3 halves. But then I have to remember that y has to equal x squared. So if x is 0, y is going to equal 0 squared. So y equals 0. So I get the point 0, 0. And similarly, if x equals 3 halves, well, y has to equal x squared. So y is going to equal 3 halves squared, which is 9/4. So my critical point here is going to be 3 halves comma 9/4. Those are our critical points, our only critical points. There are no other xy coordinates where both of these are equal to 0 at the same time. And then it's the usual process of finding capital D. So I probably should have first found fxx and fyy. Oh well, we can do it now. It's usually not too terrible. So fxx is going to equal 6x minus 0. Fyy is going to equal 2. And fxy is going to equal negative 3. Or fyx if you prefer, but also negative 3. You only need one of those because they're the same. So then capital D is going to equal fxx times fyy minus fxy squared. And I don't usually love simplifying this. So I actually really wouldn't write this out as 12x. Actually, I might. I take it back. Here I can see that no matter what I do, fyy is always positive. Fyy is always 2. Always, always. So no matter what, if I know that D is positive and I have either a max or a min, you know, it has to be a minimum because fyy is always going to be positive. Let me show you what I mean. So let's say we wanted to plug in the point 0, 0, which is not going to be fun. So plug in 0, 0, I get 0 minus negative 3 squared, which is 0 minus 9, which is negative 9. I don't actually care about the value. I just care about the sign. And when D is negative, we have a saddle. Done. Check the other point. D of 3 halves, comma 9/4. Okay, when I plug that in, I get 6 times 3 halves times 2 minus negative 3 squared. 6 times 3 halves is 9 times 2 is 18. So 18 minus 9 is positive. Okay. When D is positive, that always means there's an extra step to do. We can either check fxx or fyy at our point. Now I could check fxx. Fxx at this point, well, fxx is 6x, which is just 6 times 3 halves, which is positive. But I didn't need to, because I could have just said, instead, let's check fyy. Well, fyy doesn't matter what your point is. Fyy is always 2. So fyy is always positive, which means we're definitely going to have a minimum if we have a maximum. This function could not have had a maximum, because the second derivative with respect to y is always positive. So we have a minimum at the point 3 halves comma 9/4. All right.